Good day and welcome back for the third part of our discussion on continuity. In this video, we will investigate one example. It's a common example, and it's an example that students typically find quite challenging. And with that in mind, it's important that we pay particular attention to kind of the big ideas in understanding this problem, so if we see something similar in the future, we will know what to do. So what we are asked to do is find the values of c where the given function f is continuous specifically at the value x equals 3. And note that 3 is really the key value here because the function is defined to be one thing to the left of 3 and something else to the right of c, 3. So let me begin by just sketching a generic picture of this. It's a piecewise defined function. When the inputs are between 0 and 3, we have y equals cx plus 1. So very roughly speaking, that looks like it should be a line. So this would be the graph of y equals cx plus 1. And since I do not know the value of c, the best I can do is kind of this generic representation of a line having a y-intercept about 1. To the right of 3, we have the quadratic cx squared minus 1. And note I can't really be overly specific, but roughly speaking, I know we're going to have a quadratic, and if I just draw this with a positive c value, maybe it looks something like this. I'm just trying to get a little bit of intuition. Now, of course, the function that I have drawn is not continuous at 3. Could you tell me why? Hopefully, the limit does not exist at 3. To the left of 3, you're up here. To the right of 3, you have a lower limit value. So the limit does not exist at 3. What is it that we need to show? So for this example, we are being asked to find the values of c. Note there could be no values, one value, or more, with the limit as x approaches 3 of the function equal to f of 3. So once again, there's kind of two key computations we need to go through. And maybe starting with the easier computation, we need to determine what is the function value at 3. So looking at our piecewise defined function, if we want to know how it's defined at 3, we use that top definition, cx plus 1. So f of 3 would be c times 3 plus 1. And I find it a bit more convenient to write this as 3c plus 1. So that gets us started. But note, we also have kind of this secondary computation we need to do. What is the value of the limit at x equals 3? Or maybe more aptly stated, what are the values of c that will make this limit exist? So if we want to determine the value of this limit, we need to go back to the ideas we've previously discussed when evaluating limits. That is, how is this defined to the left of 3, and how is it defined to the right of 3? So we're going to need to investigate left and right limits. So two things are going to be needed. What is the limit as x approaches 3 from the left? What is the limit as x approaches 3 from the right? In order for the limit to exist, those two numbers, or limits, need to be equal. So if we're thinking about the limit as x approaches 3 from the left of 3 is when you're smaller than 3. You're over here. The function is defined as cx plus 1. And note, cx plus 1 is a polynomial. So by the substitution property, the limit as you approach c will be 3c plus 1. Similarly, if you want to take the limit as x approaches 3 from the right, so when you are bigger than 3, or look up here, bigger than 3, the function is defined to be this quadratic. So we replace it with that, cx squared minus 1, which is a polynomial. So the substitution property tells us the value of this limit will be c times 3 squared minus 1. And the only way the limit as x approaches 3 can exist is if the left limit and the right limit are equal to each other. That is to say, what we need to happen in this case, so I'll say the limit as x approaches 3 of f of x exists only if the limit from the left is equal to that limit from the right. Now I'm going to simplify this to be 9c minus 1. So if we go ahead and add 1 to both sides, subtract away 3c, we have c needs to be 2/6 or 1/3. When c is equal to 1/3, the limit from the left is equal to the limit from the right, and the limit itself will exist. Now we get to maybe the most important part of the problem, kind of the conclusion. And as I indicated in the first video on continuity, a common mistake is to stop early. When you've done all of, maybe we'll say, the hard work, these computations, but you don't explain how it relates back to, in this case, the question, continuity at 3. So this conclusion is absolutely necessary and a very important part of the problem, which, no, means that it's going to be worth points on future assignments. So what we've observed is that when c is equal to 1/3, the limit as x approaches 3 of f of x exists. And it's equal to either 3 times c plus 1, when c is 1/3, or c times 9 minus 1. And it doesn't matter if you choose the left or the right limit definition, because this c value is the only value where those two things agree. So this would be 3 times c plus 1. And note this 3 times c plus 1 is coming from this limit as we approach 3 from the left, which is equal to 2. And furthermore, what we know is that f of 3, if we look above at that first computation we made, is equal to 3 times c plus 1, which similarly is 2. And that's exactly what we want it to see. Therefore, the limit as x approaches 3 of f of x equals f of 3, and f is continuous at x equals 3. So just to reiterate, when we get to this c equals 1/3, if we stopped at this point, we would not have done enough. C equals 1/3 is the value where the limit exists. We need to explain, though, that not only does the limit exist, it's also equal to the function value, which means the function is continuous at x equals 3. And this would be a perfect opportunity for you to take some time and work through some suggested problems. In the next video, we're going to move on to kind of the final portion of this section on continuity and discuss one of the key kind of consequences or properties that it gives us, something known as the intermediate value theorem. So stay tuned and take care.